All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we will begin. First off, good afternoon. I am Jason Thomas, Project Engineer at America Makes, and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange webinar series, was created. Excuse me. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief Q&A session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the quick Q&A session. We will do our best to get all of the questions answered. Today's webinar is on process capability for additively manufactured Ti-64 orthopedic implants. Without further ado, it is my pleasure to introduce our speakers, Oscar Hedin and Manikanta Kondan from Oerlikon. Oscar and Manny, I will now turn it over to you and your team.
Thank you, Jason, and good afternoon, everyone. Over the next 30 minutes or so, Manny and I will present a case study on process capability in additive manufacturing based off production data generated on the RCAM Q10 Plus platform and the 3D Systems P Pro X320. And what we wanted to do is to firstly tell you about the findings from the mechanical and dimensional data analysis, then talk about our experiences of conducting the study before finally introducing some ideas for process improvements. I see a lot of familiar faces on this webinar, but just as a quick introduction to the team, my name is Oscar Hedin, and I work as an additive manufacturing application engineer with a special focus on medical devices. I've been with Oerlikon for about 3 years. However, my career in 3D printing started long before that. Prior to my current assignment, I worked for GE Additive and RCAM-AB in a similar capacity for about 10 years, and I've also held positions in the automotive industry in the fields of project management, development, and design engineering.
Hello everyone, my name is Manikanta. I'm the process engineer at Oerlikon AM Medical. I joined Oerlikon in 2017 as an intern, and shortly after that I was hired as a full-time process engineer. My areas of focus include statistical analysis on production and validation data for AM equipment, and also to provide application-specific assistance to customers on design for additive manufacturing. Prior to Oerlikon, I was pursuing my master's in industrial engineering at Northeastern University in Boston.
Thank you, Manny. For those of you who are not familiar with Oerlikon AM Medical and our additive journey, let me walk you through some quick history. Starting out more than 40 years ago as a family-run contract manufacturer serving the orthopedic industry, the past decade our company has gone through a series of transformative partnerships and acquisitions. In 2013, we entered into a strategic alliance with RCAM, granting us the opportunity to be the first company to offer EBM manufactured implants printed on the Q10 platform. In 2014 and 15, we added 4 more Q10 Plus machines to our shop and became a GE Additive's Center of Excellence for EBM technology. Following Oerlikon's acquisition of the company in 2018, we further expanded our additive manufacturing footprint to include the 3D Systems DMP platform. Today, we stand as the only medical production site in the US offering both e-beam and laser-based powder bed fusion technologies. Located in Shelton, Connecticut, our 33,000 square foot facility hosts 6 RCAM EBM Q10 Plus machines, 2 3D Systems DMP Pro X320s, and 2 Flex DMP 350 systems. That's a lot of acronyms. To put it simply, we have 6 EBM printers and 4 laser printers. And with more than 40 CNC machining centers on site, we also have extensive post-processing capabilities, and we process both metals and grade plastics. The benefit of operating a large fleet of different 3D printers is that you generate a lot of performance data that can be used to improve process control, product quality, and productivity. The purpose of this case study was to evaluate the ability of the RKM Q10 Plus and 3D Systems Pro X320 platforms to consistently produce mechanically and dimensionally sound parts in an FDA-regulated environment. The study covered two of the most commonly used titanium alloys in orthopedics, grade 5 and grade 23. The mechanical data was analyzed in accordance with ASTM F2924 and ASTM F3001 for tensor properties, and the dimensional data was collected by measuring the parts in the as-built condition. The sample data for the Q10 platform was pulled from a series of production runs of a spinal cage implant printed on 2 different EBMs in our Shelton facility. In total, more than 7,600 implants spread across 20 different part numbers were utilized for the case study. To reduce the number of variables, we only considered 2 different powder lots in this study, Lot B and Lot A. As shown in the table, both powder lots had chemical compositions to ASTM F2924 with oxygen levels between 0.14 and 0.16%. After printing, the parts were post-processed in a blast cabinet, also known as the powder recovery system, hot isostatically pressed, and then ultrasonically washed. So important to note here, all the material we will present relates to the hip condition. A few words about our sampling strategy. A grand total of 38 EBM builds were produced, 18 of which were printed on machine number 1, and the remaining on machine number 2. Our mechanical inspection plan for lot release requires 4 test coupons to be printed with each production build. So the total number of printed coupons was 152. Not all of these coupons are used for actual testing. 2 out of 4 coupons are then sent to a third-party test lab and our mechanical properties. 1 coupon is also sent for chemical analysis and microstructure characterization. The remaining coupon is kept for retesting purposes.
Thank you, Oscar. So similarly for laser beam, we used 2 3D Systems Pro X320 machines for the study. We analyzed 2,600 parts across 29 builds, and all the parts belong to one single cage family. The powder lot used in the study is a titanium 6-4 grade 23 to ASTM F3001-14. The table on the left-hand side of the screen shows the chemical composition of the powder lot used. A total of 160 were printed across 29 builds. As you can see on the bottom left corner, that's our build volume. We use 4 coupons on 4 corners of the build plate, and we test 3 of them for mechanical testing and 1 for microstructural testing. A grand total of 116 coupons were printed and analyzed in the study. The microstructural coupon is not showed in this picture since it's an IP of the customer. Before we go into the analysis, I would like to clear up some concepts that will be useful in the further slides. Process control and process capability are the 2 metrics we used in the study to analyze our process. Process control is a measure of stability and consistency given process. This indicates the repeatability of the process. We analyzed process control using X-bar R charts in the study. Process capability is the ability of the process to meet the specification limits. This indicates the reliability of the process to meet specification limits provided by the customer. The indices used for process capability analysis are the CPK and PPK values, the Z-scores, and also we try to quantify using defects per part per million.
We'll now look at the mechanical test results. And in the first part, we're going to focus on the EBM platform. True picture of our process capability, we first need to know if the process is in statistical control, as Manny mentioned. To that end, we use two types of control charts, X-bar charts and range charts. The X-bar chart plots the average value of bonds tested in a build versus build number. And the purpose of the X-bar chart is to check the existence of trends in your data, such as fallouts, center shifts, and linear trends. For machine number 1, the process appears to be consistent and predictable. In the 18 builds that were printed, we had 0 test failures. And while there are points beyond the control limits, the process averages remain stable and above the specification limits given by ASTM F2924. So the X-bar charts are in statistical control. To calculate CPKs, we also need an estimate of the process spread, and that comes from the range charts. The range shows the difference between the maximum and minimum value in a build. So the range is a measure of the variation within that build. Now, for machine number 1, the within build variations are small and consistent. So also the range charts seem to be in statistical control. Final check, we need to verify that our data set represents a normal distribution. There are many ways of this, but one way of doing this is to draw a normal probability plot, calculate the so-called probability value, and see if the p-value is greater than 5%. In that case, the data should essentially fit a straight diagonal line. As shown, the plotted data points seem to line up, and the p-value satisfies the conditions for normality. Consequently, the tensile data for machine number 1 can be considered normally distributed. So with the control charts and normal probability plot in good shape, move on, draw histograms of our process data, throw in the specification limits for ASTM F2924, and calculate our CPKs. If we do this, we'll discover a couple things. First of all, for a manufacturing process considered capable, typically a CPK of at least 1.33 is desired. Our CPK values are always greater than that. As a matter of fact, the Z-score, which is another way of expressing process capability, exceeds 4.5. And the projected scrap rate is less than 3.4 parts per million, which is equivalent to a 6 sigma process. If we turn our attention to the second machine, we will see a similar pattern emerge. From the 20 builds that were printed, a total of 40 coupons were tested with no test failures reported. The process averages largely remain within limits, and there are no signs of center shifts or linear trends. However, the process spread for machine number 2 is a little bit higher, and we also have a few outliers. As a result, the Z-score for machine number 2 hovers around 3, indicating that the process performs at a sigma level of approximately 4.5. Here we've dashboarded the Z-scores for all tensile data for both machines to see how they match up against each other. A small machine-to-machine variation can be seen with machine number 1 performing significantly better than machine number 2 on yield strength. With that being said, both machines are highly capable of meeting the ASTM F2924 specifications at a sigma level of at least 4.5. To further monitor the process, we also perform 100% mechanical inspection of every production build, and this gives us additional assurance that the parts will be within spec. So to summarize the mechanical test results for EB, a grand total of 76 coupons pulled from 38 different builds were tested for tensor properties, with all tests yielding passing results. While outliers do exist, the process averages remain stable and, more importantly, well above their specification limits. The process capability metrics for each machine are always greater than 1.33, except for yield strength for machine number 2, suggesting that the process is conditionally capable and requires adequate controls to continue to produce in-spec parts. One of the controls we've put in place is close monitoring of oxygen content in our powder lots. This graph shows the correlation between tensile properties and oxygen content in printed Ti-6-4, and it indicates that there's a minimum oxygen level that we need to stay above in order to meet the ASTM F29 requirements. And this is a really important finding from this study. There's a pretty tight range oxygen that we need to stay within to reliably meet ASTM F2924.
Thank you, Oscar. Similarly, we did the process capability analysis for the laser machines as well. For the first laser, we plotted the X bar R charts to make sure our process was under control. Based on the X bar R charts, there was no flags raised in the process, which we can determine that our process is under control. We also analyzed the R bar charts to make sure there was no wide spread of data or any unusual causes of variation. After checking the first two boxes, we went ahead and calculated the normality of the data. When we look at the normality of the data, the p-value was always greater than 0.05, which indicates that our data is normal, which is another indication that we can start our process capability analysis. So we plotted the histogram and also included our specification limits. Here, the specification limits are slightly different than 2924. They're actually lower. So the specification limit here is 795 megapascals for the yield strength. So once we put in our specification limits, we have a CPK value and PPK value greater than 1.33. And also the z-scores are greater than 4.5, which indicates that the process is achieving a Six Sigma level. Similarly, we did similar analysis for the machine number 2 as well. We plotted the X bar R charts. We do see 1 point going out of the upper control limit. However, that's just a flag in the process, but that is not a clear trend that there was something wrong with the process. And also we checked for the R bar charts to see the variation in the data. Again, these two charts look well and under control. Proceeded with calculating our normality of the data. Even here, we observed that the data was very well under the normal distribution. So we went ahead and calculated our process capability indices. Here as well, the CPK and PPK values were well ahead 1.33, and the z-scores were also greater than 4.5, indicating a process which is Six Sigma level. So in summary, dashboarded all the z-scores for all the mechanical properties for each machine 1 and machine 2. One thing to observe is both machines are very similar to each other in the yield strength and the ultimate tensile strength and percentage elongation. However, we see some variation in percentage reduction, but that does not stop us from concluding that these machines are highly capable to meet the specification limits provided by the ASTM standard. Also, for additional assurance, we do 100% mechanical inspection to make sure we are always producing good parts. So in comparison between EBM and laser beam, just to be clear, our aim here is not to endorse one technology over the other. The goal here is to prove, irrespective of the technology used, we are able to achieve a Six Sigma level process. We do see on EBM, on machine 2, where we have a lower z-score on the yield strength, but that does not mean that the process is not capable of achieving the specification limits. When there is additional work to be done and more controls to be included, but the process is nearly performing at Six Sigma for every machine we analyzed. However, as a side note, the laser data definitely shows a nearly Six Sigma process and very similar results from one machine to the other.
We're now going to switch gears a little bit and move over to the dimensional data analysis. Our in-process inspection plan for this implant calls out a number of dimensions, including overall height, width, and depth. Since the measurements are taken as printed, we've implemented pretty generous tolerances, plus minus 0.4 mil in all directions. The implants are grouped into two categories, small and medium, based on their footprint size, with the overall dimensions ranging from 5 by 14 by 12 mil for the smallest footprints, up to 12 by 17 by 15 for the largest. As a side note, all in-process inspections are currently carried out manually, and with a 100% inspection requirement, this effort can become both time-consuming and labor-intensive. So there are significant gains to be made if we can reduce the inspection burden. And just to get myself out of trouble here, the image shown here does not depict the actual customer part. It's just a visual representation of a generic spine implant. These process control charts show measurements of the X, Y, and Z dimensions for one of the high, medium, size 8. And the corresponding process capability metrics are listed on the right-hand side. As shown, the distribution for the measurements is centered around the mean, and the groupings are, which is indicative of a highly controlled process with small part-to-part variations. Build-to-build variations are also small, as indicated by the fact that the CPK and PPK values are very similar. They're almost equal. In some cases, however, exhibit lower process capabilities. Notice how the top chart shows an offset from being mean-centered. But the measurements are still very repeatable. As long as the process remains consistent, we can solve the center shifting by simply rescaling the affected models. And this is important because it illustrates a recurring problem in our AM production, the need for part-specific scaling factors. This graph shows dimensional deviations from nominal for a range of smaller sized implants, which were all printed on the same machine using identical scaling factors. For a given scaling factor, the X dimensions of certain footprints tend to err on the low side of nominal, while others are slightly oversized. Others still are right on the money. Our engineers deal with this problem by running dedicated scaling builds as part of the qualification of new products, which is a costly and time-consuming process that we would certainly like to avoid. Unfortunately, the thermal effects leading to these shifts are still not very well understood. Another challenge we frequently face are systematic measurement errors on account of part orientation. Overhangs and negative surfaces are inherently difficult to measure due to the increased surface roughness in these areas. And to make matters worse, the print for this plan calls out dimensions which are directly related to how well the operator has leveled the build plate. If you think the distribution for the Z dimensions in the bottom right chart looks bimodal, you're absolutely right. The two groupings represent different builds where the initial build plate setup has adversely affected part size, rendering one batch of parts undersized and the other oversized. And this highlights the importance of choosing robust quality features for inspection. Why is this important? Why do we care about process capability, CPK, PPKs? Maybe we don't. Well, I do, and I'm sure Manny and our process engineers do, because a capable and stable process allows you to reduce your inspection programs. Now, as the summary of process metrics for machine number 1 and 2 makes pretty clear, we still have a ways to go before we can claim C1.33 across the board. But what looks like a pretty discouraging set of data at first actually turns into a plan of attack if we look at it through the eyes of a process engineer. In most cases, a low CPK is related to high center shifting. Consequently, to improve process capability, we can shift the dimensions back to nominal with a rescaling effort. We also seem to have a directional bias in our measurements. Z dimensions, for instance, are consistently less stable than other dimensions, regardless of part number or machine. So let's make sure our inspection plans call out robust inspection features. And just to be clear, the values highlighted in red here do not necessarily mean that the parts fell out of spec. They highlight and indicate areas where we need to improve our process capability if we are to go from 100% inspection sampling plans. My point is, continuous improvement is an iterative process, and statistical process control, such as this study, is our guide along the way.
Thank you, Oscar. So let's go back to the concepts we discussed earlier before starting our presentation. Our goal was to stay in the quadrant where the process is under control and capable of meeting the customer specified specification limits. We looked at the mechanical data for EBM and laser beam and observed how the process can achieve a Six Sigma level. Controlling the oxygen content in the powder is a key for good and consistent mechanical properties of the parts as well as the coupons. And process and use of statistical process controlling tools are a key in any production and manufacturing environment to achieve a highly capable and a controlled process. We also identified some key areas of improvements. Equipment advances. Today, the AM equipment and their performance is highly dependent on the process controls in place. In future, we expect the machines to be more smarter to adjust for slighter variations in the environment and the process to make sure they don't lose the state of control. Prediction of scaling is a tedious process, takes a lot of time and development. An application engineer would be very happy if a 3D modeling software can help him or her to determine the amount of distortion happens during the build. This will heavily help any engineer to estimate the amount of distortion in the parts and also save development times and costs. And another area of improvement for post-processing. Most of the AM implants today need secondary machining or some sort of secondary processing. Especially when designing for AM, it is highly recommended to include critical to quality features that will be further helpful during the machining or secondary processing of the implants.
At this point, I'd like to turn the presentation back to Jason and American Makes for the Q&A session.
All right. Thank you, Oscar and Manikanta. We will now head into the Q&A session. If you do have a question for our presenters and you haven't done so already, please type it into the Q&A box. So we do have a couple questions here. We'll start out with, so was this done under standard hip conditions?
Yes, it was done under standard hip conditions provided by the ASTM specifications.
All right, great, thank you. All right, another one here. How many qualification builds do you build, and how do you determine the type of specimens required to accurately characterize the build envelope?
You want to tackle that, Manny?
Yeah, sure. So we determine the number of builds. We actually determine a confidence level. We work at a 95% confidence, and to achieve that, we associate a number of coupons so that we can achieve the 95% confidence. And how we determine the specimens is we go by the FDA guidelines on using how to develop our qualification builds. For example, we put all our coupons in the extreme corners of the build. We build vertical coupons, horizontal coupons, and microstructural coupons to analyze every mechanical element of the part.
Okay, thank you. All right, so we have another one. The hipping was to make both the same, or do you need hipping in both processes?
Well, so first of all, hipping is actually it's a recommendation, maybe even a guideline per the ASTM standards. It's more a requirement for the laser process because we have a lot of residual stress, whereas the EBM process is a hot process. So there's not really a need for thermal processing at all, but just be compliant with the ASTM standards, we still HIP, and we're all about compliance here.
Okay. So let's see. All right, could you please comment on dimensional analysis as built versus after HIP? On 0.4 millimeter for a height width length is fairly easy to print to. What about features like holes and slots that probably need 0.1 millimeter or point or minus 0.2 millimeter?
Yeah, I think if we can divide that question maybe into two parts, I'll start with commenting on the first part. We do not see any major or distortions before and after printing, mainly because these are very small parts. They're not very massive parts, they're medical parts. So as a matter of fact, we sometimes elect to ship parts out for hipping after separating them from the platform because we're so confident that we're not going to get any distortions. I don't know if you translate that to more bulky aerospace parts, you might get other results, but we don't see any major distortions before and after HIP. And then you'll have to remind me what the second question. Okay.
So I can take the second question, Oscar. So I know it was mentioned that a plus or minus 0.4 is a fairly wider tolerance compared to plus or minus 0.1. You're right in some cases, but have to understand how consistent we are with that tolerance limits. We can get down to a plus or minus 0.1 or 0.2 if we have a repeatable process in place first. And also, I understand plus or minus 0.4 is wide, but at the same time, try, when we are dealing with the number of parts that's like close to 10,000, which is close to a year and a half of worth of work. It's pretty, the tolerance band gets pretty narrow at that point. And for holes and other features, we have analyzed them during our qualification builds, but we did not include them in the study yet.
And just to add on to Manny's comment, I think a lot of, if you're not from the industry, you may not understand that a lot of these parts have a very complex random lattice structure on them, which makes repeatability between the measurements a challenge as well. And that's also a reason why we have such a generous tolerance band.
All right, so we're getting quite a few questions in here. See, did you follow the IQ, OQ, PQ process for qualification and any design experiment screening process parameters?
I can take that, Oscar. So we do any process parameter development or any experiments on them, but we also try to do some DOE on some of the factors we can control, like the powder oxygen content and other parameters which could affect the mechanical properties. But we do not touch any of the process parameters provided by the machine manufacturers. And yes, we do follow the IQ process for qualification.
All right. Let's see. So what are the key metrics you feel need to be brought under control to move away from 100% inspection?
Yeah, I can take that one. I think that goes back to this goes back to kind of the whole process chain. When developing a new additive manufacturing platform, I think the OEMs need to think about the end of the technology, and it's not just about, it's true that with additive manufacturing we can create very cool designs, very complex designs, but after printing, most parts are not ready for service. Typically, there's some kind of post-processing step, either thermal, mechanical, and chemical. And as an end user, as a contract manufacturer, we don't necessarily in the business of developing all these parameters. So what we would be looking for are more end-to-end solutions. Someone brought up the subject of HIP and thermal processing. I think those are topics where we would see more from the OEMs as well.
Okay, let's see. Do you feel that standard E8 tensile samples are adequately representative of the material in the implants themselves? Are the parts, especially the lattice and pores, produced with the same processing parameters as the tensile samples?
You want to take that, Oscar?
Yeah, I can take that. The answer is it depends. It depends on the process. For some of the processes, especially the laser powder bed fusion system, my understanding is that you're typically using the same laser parameters for both the lattice structure and the bulk part, the solid part. It's not necessarily true for E-beam, where you might have different parameters for the solid part and the lattice structure. I'm not sure if I quite got that question, but I hope I answered it.
Okay. And what is the tool that you use for dimensional accuracy?
At this point, we primarily use, it depends on the product. If we look at the spinal cage implants, which are essentially high mix, low volume products for us, I mean, just one of these products families can include hundreds of part numbers. It's not very cost efficient for us to develop automated solutions. So typically it's manual inspection, overlays, calipers, things like that. But of course, we are looking into automated solutions for that as well.
All right. So let's see. Could you please comment on dimensional analysis as built versus after hip?
So I can take that. So we did not analyze in this round for as built versus after hip, but prior to this, we did have some qualification builds, and we saw a negligible amount of change from as built to after hip conditions and dimensions for the parts.
All right. See, can you elaborate on what you mean by scaling factors for dimensional data?
Yeah, sure. So especially working with an EBM platform, there's always an avenue for your parts to shrink during the process because it's a hard process. So to compensate that, there's something called as a scaling factor. And how I calculate that right now is by physically building the parts or measuring them and multiplying them with the delta to achieve those scaling factors. I hope that answered the question. Yeah.
All right, let's see. EBM machines work on vacuum atmosphere. Some use usually argon flow. I know it is possible to control oxygen inside the chamber. What was the oxygen level inside the SLM chamber?
For the DMP machines, it's close to 3 parts per million. And the EBM is, of course, is vacuum.
Okay, thank you. Let's see. Can you please elaborate on your views on control for quality features?
Sure. So when I said control for quality features is you want to establish some kind of in-process inspection steps where you're sure that your part is actually printed so that it can be machined and achieve the final level or the final leveled part. So in some cases, when you print the parts, there's obviously a need for machining of it. And you want to pick some dimensions which indicates that even after machining, your part is going to be within specification limits. So that's one of the reasons why you have to choose your critical to quality features during in-process inspection to make sure your parts will be inspected during in-process inspection and also after machining.
Okay. Do you believe replicating the tests covered here on a non-hip study will be performed in the future? a foundational study such as this could change industry process paradigms?
So do we believe that a similar study will be done on material before hipping? Was that the question?
I think that's, yeah, I think so. So yeah, I'll read it again. Do you believe replicating the tests covered here in a non-hip study, yes, will be performed in the future?
I think for us internally, it would definitely be make sense. I think what's really needed is the industry standards surrounding additive manufacturing. They need to be more mature, and they need to be developed a little bit further. I think ASTM and a lot of these bodies are working on that, but essentially that's the biggest hurdle for us right now for going from a hip condition to a non-hip condition, because we're a contract manufacturer, and essentially we need to follow the ASTM standards that our customers impose on us, and those dictate hip as of now. But yes, to answer the question, yes, I think a study will definitely be done. We'll definitely see results from that in the near future.
All right, can you describe the process of identifying individualized scaling factors?
Yep, so our process is pretty simple. We build the parts, we get the dimensions, and based on the dimensions orientation in the build platform, we determine our XYZ scaling factors, and then we apply those scaling factors in the next build and build the parts again, and we get the measurements of the newly built parts. Again, I think we mentioned this before, as this is a tedious process, and that's one of the key takeaway is, if there's a 3D modeling software which can estimate the amount of shrinkage that can happen in the process, would be quite helpful in a development time and cost perspective.
And just to expand on that, I know there's software solutions out there that do claim that they can predict and compensate for thermal distortions. What we've seen is that they're not accurate enough for our needs. So hopefully that will come in the future as well, because this will definitely be an area of interest for us.
All right, thank you. All right, let's see. Next question. I think this will make sense. What was the build plate orientation?
Depends on the part, to be honest. So on one of the pictures, I think Oscar showed the X, Y, and Z dimensions. So Z is facing the build plate downwards, and X and Y depends on which way you orient your part.
Okay. Let's see. Have you looked at dimension differences between center and corner points?
No, we haven't specifically targeted that as part of our scaling builds. But what we have noticed is that they are pretty consistent across the build platform. I think the only situation where you see some differences is probably when you look at in EBM, you can actually stack parts in multi layers. And if you look at scaling factors between different layers, they tend to change as well.
All right, thanks. All right, we just have a couple more here. Do you machine the tensile coupons?
Before testing, yes, they get machined dog bone structure.
Thank you. And our last question here. Scaling an XYZ based on height, width, and length is certainly acceptable. Is there evidence how other features such as holes, slots, or counterbores, etc., are affected by scaling?
The answer to that question is, again, it depends. It depends on the geometry. If there's a large change in cross-sectional area across the part, and so to speak, the solid mass change as you go along the z-axis, yes, you might have differences. We generally, for these spine cages, the parts are rather they're rather thin and not as much affected by thermal distortions in that manner. So for our purposes, we've seen that just scaling in X, Y, and Z covers most of the ground here.
All right, well, we got a couple more questions come in. So while you're answering that one, so we do have some time left. Would you recommend lot release tests per build, or is this not necessary?
I mean, based on the based on the presentation we just had, it definitely says we do not. But at the same time, these are human implants, and every implant goes into a human body. And if I were the patient, I would be a bit paranoid. But at the same time, we want to have the process where it is so consistent that we never have to go back to lot release testing. But at the moment, we still do lot release testing.
Okay, thank you. Let's see. The difference in RA between machines was, I'm sorry, the difference in RA was high between machines. Why? And how do you explain it?
So another key difference was on the laser beam, we used a Eli powder, and on the PBF we used a non-Eli powder. Those two materials have quite a different percentage reduction in value, both in the standard limits and also the observed values. So that's one of the reasons why we saw the difference. But we are still evaluating if we use similar powder lots, how they would be reacting to percentage elongation and also percentage reduction in area.
All right, thank you. And this is going to be the last question. What inspection method did you use for evaluating the X, Y, and Z dimensions reported in your data?
We used manual inspection methods, so calipers and relays.
All right, thank you. All right, so that'll wrap up today's TRX webinar series. I would like to once again thank Oscar and Manny. If you have any further questions for our presenters, please reach out to them directly at the email that is on your screen. It's am@orlic.com. There will be a post-webinar survey going out to all those who participated. We do really appreciate the time that you take to provide America Makes feedback so we may continue to improve and strengthen the additive community. And a reminder that if you think you or your organization would be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thank you very much. Have a wonderful day.